This is a video to cover some introduction to basic simulation modeling. And the example I want to use is a retirement planning example, which is used in chapter 1 and 2 of the book, but I'm going to extend it quite a bit further than what's shown in the book. So to start with retirement planning, if you think about trying to visualize the problem, there is one issue that you'll face anytime you're trying to build a model where time is an important dimension, as it is in retirement planning, because you are presumably working now and planning for retirement later in life. So the time dimension is kind of important. I have a lot of trouble trying to build a visualization that takes into account time as well as the structure of all the pieces of the problem. Usually, I have had to choose one or the other, either model the time dimension and not the entire problem, or model all the pieces of the problem and abstract away from the time. It's not that it's impossible to do both, but I usually have a problem trying to figure out how to do both. So I'm going to choose, the time dimension seems essential to me. I'm going to choose to focus on that in my visualization. And it won't be a complete visualization of the problem, but it'll capture, I think, the essence of the most basic parts of the problem. So here's my visualization that takes into account time. What happens as time goes on? You start off at some time period with a retirement fund, and as a basic question, are you retired or not? If you are retired, then you have to start withdrawing some money from it in order to live on. Depending on how much you withdraw, there's a certain amount left, and when the rate of return gets applied to that, you see what your retirement fund is the next year, and then that becomes the starting retirement fund for T+1, and you go through it again. If you're not retired, then several things happen. You have a salary level. You may get some raise on that. That determines what you had a salary level from last year. You may get a raise for a salary level this year. Based on that, you make some contribution. Your employer generally will provide some kind of matching funds that gives you a total contribution to your fund, and that when you add that to the initial fund, you get what the retirement fund looks like next year, which gets a rate of return applied to it, and then it becomes the starting for the next year. So every year, this essential structure has to be captured, and the basic model looks something like this. We have some basic inputs here, which I'll come back to. All of these are interpreted as adjusted for inflation. So if I look at an annual raise of 2%, that means 2% above and beyond inflation. Expected inflation is on the order of 2 to 3%. So we're talking about raises of 4 to 5% per year. The rate of return is adjusted for inflation. Most investment analysts, we probably use 5 or 6% now as an expected rate of return, but that includes inflation. So when you take inflation out, maybe like 3%. The retirement living expenses, now you may not retire for 30 years, so what's the cost of living going to look like then? Well, adjusted for inflation in today's dollars, let's say that you anticipate it being $50,000. And in this model, let's start off with this being your current age 30, a retirement age of 65, and starting off with no retirement fund, you're just starting it out. So the logic of the model, which captures what that visualization shows, let's just pick one of these ages here. Depending on what your current age, what you can change that. If you change the current age, it will adjust all of these age figures. The first question is, are you retired? And all you do is compare this age that's in A16 to the retirement age, which is in B11. If you're not retired, well, in any case, you have a starting fund level, which is the fund at the end of the prior year, which starts off at 0, but in this case, right now, 8,500 is what's in there at the end of the first year. There's a return on that. And now, as long as you're not retired, you're going to earn salary. So you notice in the salary formula, we're applying the initial salary, some raise for some number of years to it. But the main thing is this first part, 1 minus B16, which is basically saying, if you are not retired, there's a 0 for B16, you're going to get that salary. As soon as you are retired, when you are retired and your age is above the retirement age, you've got 1 minus that. So if you're retired as 1, you're multiplying it by 0. That's why you zero out the salary. Once your age goes above retirement age, you're not earning salary. below it, you will be earning salary. Then you have, based on the salary, an employee contribution, an employer match, and a total contribution. Notice when you are retired, you don't get any, you don't continue to contribute, and your employer doesn't continue to contribute. But once you're retired, you start withdrawing funds. So the B83 number, or the column B number, retired or not, shows up with the withdrawal. As long as you're not retired, you're multiplying some living expenses by 0. You don't get anything withdrawn. And as soon as you are retired, you do multiply the retirement living expenses by 1. And so you start withdrawing funds. Then the fund at the end of the year is simply looking at what you started with, what you add to it, what the rate of return is, minus whatever you withdrew from it. And that'll give you a fund at the end of the year. And then there's a 0-1 cell. Are funds still available? As long as it's greater than 0, funds are still available to you. When it goes negative, they're not available. So the objective here is the year that funds run out, which will simply be add to your age how many 1s there were in column K, and that'll give you what year they run out. You'd have to uncover the hidden rows here to see that it's actually at 83 that this happens. So there's a basic retirement model. One other issue with the retirement model is the objective, well, let's say take retirement age as an example. Is retirement age a decision you make? Is it an uncertain variable? Is it an objective? It could be any of those 3. Many of us plan for retirement thinking it's a decision. We will decide when to retire on the basis of how much money we have and other things. Some people are forced to have retirement age forced on them. They either lose their job and can't find another. Health forces them to retire. It could just be an uncertain variable. It could also be an objective. You may be planning to try to retire at age 62, and so it may be something you want to make your retirement age as low as possible, given that you need a certain amount of money to live on once you retire. So retirement planning is a strange sort of model, because usually it's clear what the decisions are and the objectives, and here we have a variable that could be a decision, could be an objective, could be uncertain, or some combination of those. Similarly, retirement living expenses, that's a decision. You decide whether you're going to travel a lot or not, or how expensive your home's going to be, or what part of the country you live in. At the same time, there are things beyond your control. Your retirement living expenses might include a lot of medical expenses and are not covered by Medicare, and you didn't plan on, and so that could be an uncertain variable. Or it could be an objective. You could say, my objective is to be able to retire and have $70,000 a year to live on. That's the lifestyle I want to shoot for. So in retirement planning, a lot of these variables, it's not clear how to view them. And it really depends on the context. And if you were doing it, advising somebody, I think it would be important to determine what type of variables these are. For my purposes here, I'm going to treat the retirement living expenses as uncertain. It's largely beyond your control, that you kind of planning right now on $50,000, but it could be lower than that, but there's still some chance it could also be a fair amount higher than that. And the rate of return is clearly uncertain, because everyone knows past performance is not a guide or a guarantee of future performance. The rate of return is essentially uncertain. There are other things that could be uncertain here. What is your raise? I mean, there's no guarantee you'll get a raise, and how big it will be is uncertain. But for purposes of showing how simulation works and how we handle uncertainty, I'm just going to treat these 2 as uncertain variables, and everything else here as fixed. And my objective is determine what year the funds run out of money. So how do we handle uncertainty? One way we could do this is under what-if analysis to go to a scenario manager. Let's add a scenario. We'll call this the pessimistic scenario. And we will change cells B7 and B8. Okay, what do we want to change them to? Well, what's the worst case scenario? The worst case scenario, let's say, is that I can only get a 1% rate of return adjusted for inflation. And the worst case scenario is I'm going to somehow have to spend $70,000 a year, largely from unplanned or uncovered medical expenses. And how good could things be? Well, my optimistic scenario, changing those same cells, will be that we get a 6% return. That means with inflation, it's 8 or 9%, maybe even 7%, let's say. And we will only need $40,000 to live on. If you, and these scenarios can be as complicated as you want, so you could vary all of these numbers to sketch out these scenarios. That's one of the advantages of scenario analysis, is you can make the scenarios as rich as you want. And if you click summary, what cell do we want to focus on? Well, we'll say our objective, the year funds run out. You get a nicely displayed scenario summary here that basically it could be that you could run out of money at age 72 all the way to 101. 101 is as far as this model goes. You'd have to, if you're going to run out at age 140 or something, you'd have to extend the model further to find that out. So it's nicely displayed. The nice thing about scenario analysis is the scenarios can be as complicated as you want, but that actually points to why I think they're not very useful for planning. And that's that there's no way of assessing how likely these things are. If the tendency would be to interpret this as, well, given these uncertainties, my funds will last anywhere from age 72 to 101. Does that mean it's impossible for you to run out of money before 72? Or is 72 just as likely as 101? Is one of these more likely than the other? How likely are they? There's no information to judge that on. And the more complex the scenarios get, the harder it's going to be to determine that. Even if you got this information by saying, what rate of return do I think there's only a 5% chance it could be lower than that? And the answer is, you say, I think 1%. There's 95% chance I'll get at least a 1% rate of return adjusted for inflation. And I think there's at least a 95% chance that I won't have to spend more than $70,000 a year to live on. Well, if these are independent of each other, you've just sketched out a scenario that actually is only a 5% chance it could be this low and a 5% chance it could be this high. 5% of 5% is pretty close to zero. You've sketched out a scenario that almost can't happen, even though there was a 5% chance for each of these. That's if they're independent. It's more complicated if they're related to each other. So, you know, I guess if you were asking somebody for a 5% pessimistic scenario, you'd say, what combination of these things do you think there's only a 5% chance it could be that low? And I think most human beings would be incapable of giving you any kind of meaningful judgment on that, especially if you have more. Even with 2 input cells, I think it would be hard. If you had more, it would be really impossible. How do I know what combination of rates of return and living expenses is a 5% chance of it being that low or that high? I don't think I would have any information on that. So this gives you, its downside, I think, is that it appears to give you useful information, but I don't think it really is useful. So let's go back and see, can we do this some other way? Well, another tool we could use is we could enter these possible values, like the $40,000 for retirement. Let's go 45. Let's go all the way up to 70 as possibilities. And then let's enter rate of returns from 1% up to 7%. And put up here our objective, which is cell C11. Then highlight this entire range of cells, and under what if analysis, go to a data table. The row input cell is we put the values on this top row. Where do we want to use those values? We want to use that for the retirement living expenses. The column input cells, where do we want to use these 1 to 7% values? That's for the rate of return. Click OK, it fills in the table. This one actually, I think we need to reformat. And what might make it a little nicer to look at is to go and do some conditional formatting. Let's highlight where it is less than, if you're male, expected lifetime is 81 years. If you're female, I think it's 83. A nicely formatted table. Here's your trouble areas is red. And anything that's not red means that the fund lasts at least as long as your expected lifetime. So this is kind of more detailed, more granular information, but it still leaves a lot to be desired. For one thing, anything that's not in red means the fund lasts as long as your lifetime. Well, right here, this lasts exactly your lifetime. So there's probably about a 50% chance that you will live longer than your expected lifetime. There's only a 50% chance the fund's going to last as long as you live in this cell. But what about this one? That's more than a 50% chance. How much more than 50%? Is it 60%? Is it 90%? I mean, there's no information, again, probabilistically. So while you have more granular information, how safe you are, even on these 101s, it seems to indicate as if you don't have anything to worry about if you get a 5% rate of return. Is that really true? There's nothing to worry about? Is there no chance? I mean, very few things in life are certain. And the list is usually taxes and death. It does not include rate of return on your retirement funds. That is not one of the certain things in life. So it looks perfectly safe, but it's not perfectly safe. How safe is it? We don't know. So there's no information in this to give you information on how likely it is. So if we want to get some probabilistic, more meaningful information, let me just clear that out. And clear out the color. Oops, clear the color there too. So simulation modeling works differently. It basically says, let's assign probabilities to these things. So let's look at retirement expenses and say, not just what are some possible values, but how likely are those values? So let's go under at risk to define distributions. Retirement living expenses, we don't really have any data to work from, so maybe what we should do is say this is kind of a subjective judgment. Nobody really knows what you'll need to live on. You may have an idea what you'd like to live on, but the uncertainties could make it larger or smaller. For judgmental uncertainties, and we have an entire chapter dealing with how do you choose these distributions, but a common one to use, the most common one for judgmental variables, subjective judgment, is a PERC distribution. If you select this, basically want to know what kind of values could it take on. Well, let's say that the minimum, and good modeling, you would put this in a cell, not type it into this box. You would have a cell address you would point to, but for now I just want to show you how the simulation works. So let's say it could be as low as 40,000. The most likely is that it's 50,000, but it could be as high as 70,000. So if you look at what this distribution looks like, you'll notice it's not symmetric, it's somewhat skewed, because the upper end was further away from the most likely than the lower end is. 90% of the time, it'll be between 40,285 and 61,399. But 5% of the time, it'll be less than that, and 5% of the time higher than that upper value. This is a probabilistic assessment of possible living expenses. there is a fair amount of work that goes into trying to get these to be sort of more reliable figures. Usually you would like to talk to some expert, or in this case, the expert really would be your client if you're an investment advisor. And there really is sort of an art to collecting this information rather than just giving them a piece of paper and say, give me 3 numbers. You actually want to make the context as real as possible, characterize what uncertainty you're trying to get them to give you some estimate of. And very often it's good to collect this information from more than one person, because different people have different judgments, and collecting multiple sources of information might make it more reliable. So we go into detail in the book on different ways to collect this, but basically once you have determined a distribution for this, it basically is going to say, well, it can vary anywhere in this range, but it's most likely in the middle. The nice thing about the PERT distribution is, if you think about sort of answering these questions, what is the minimum, most likely, and maximum? Most likely probably is going to be a little more confident response than what the minimum and maximum are. And minimum and maximum themselves, does that really mean absolutely the minimum, it's impossible to be lower, or realistically it can't be lower? And what does realistically mean? That there's only a 1% chance it could be lower? So people have trouble with minimum and maximum, whereas the most likely, they feel a little more confident in their estimate of it. And the PERT distribution is most sensitive to the most likely value. If you make the minimum value, instead of 40,000, let's say you change that, I'm going to change it to 20,000, and watch the shape of the picture when I hit enter. It has pulled the left-hand side down, but you can see the bulk of the distribution is still up around 50,000. Oh, I moved it down to 2,000 even, 20,000. So even pretty big changes in minimum and maximum don't affect most of the distribution very much. So the PERT distribution is not very sensitive to the minimum and maximum values. It really is driven mostly by where the most likely value is. Once you get a distribution you want, if you click OK, it has put that into the cell. Notice the form of this, it's an Excel function. All the at-risk functions start with the word risk. So it's an at-risk function. What kind of function? It's a PERT distribution. PERT distribution has 3 parameters. Those are the ones we just entered by hand. Those could be cell addresses. And the risk static is basically just saying that if you're not running a simulation, what value should appear in the cell, and that's our starting value of 50,000. You could change that to anything you want. That would be just what appears when you look at the spreadsheet. Let's look at the rate of return. Now this one's a little different. We do have data on rates of return, and we will actually see that at risk will tell us or give us an idea what distribution to use. But for now, I'm going to use a distribution that you shouldn't use for rates of return. I'll use a normal distribution. It is pretty common that people use normal distributions to approximate rates of return. It's not the best choice, because the normal distribution basically is a bell-shaped curve, and everything, 99.7% of the time, I think you're within 3 standard deviations of the mean. So you're almost never going to get something more than 3 standard deviations away. Whereas you may have heard that people refer to the stock market having 6 sigma events, means 6 standard deviation changes on a daily basis. Those happen far too frequently for a normal distribution. So the problem with the normal distribution is the tails, the end of the distribution, are pretty thin, and most stock market data, you actually want thicker tails than that, because the more extremes, both on the positive and negative side, happen more frequently than a normal distribution would. But for now, I'm going to use a normal distribution just as an example. Select it. Oh, excuse me. Let me do that again. Let me enter. We use 3% as the mean, but the standard deviation is actually quite large. And if you look at data, it's on the order of like 17% per year. which means in any given year, the rate of return could be 25% reduction to a 31% increase. On average, it goes up. And over a long period of time, this has been true of the stock market. In any given year, it's certainly within reason, your 5% chance it could go down by 25% during that year. But it could go up 5% chance, even more than the amount it could go down. So it's really quite uncertain, and that's what we'll put into this cell. Now, to do a simulation model, really all you need is one or more cells that have distributions to govern the uncertainty. It helps to tell at risk what you want to focus on as an objective. And since this is the objective, I'm going to click this Add Output button. Make sure the title is what you want it to be. It picks up whatever title it can associate with that cell. So it looks at actually the row label and the column label. But it's really the column label we want, just the objective. Your fund runs out. You'll notice what it's done to the formula. It has added to the existing formula a risk function, risk output, just telling it, use this as an output, which means collect information about it when you're in a simulation, and call it year funds run out. Funds run out. We are set up to do a simulation now. If you look at these buttons here, first of all, there's a button here. This little second button is a dice button. And if you click that, it will randomly pick, in a sense, a scenario from the information we gave it. So what's shown right here is actually a 3% reduction in the rate of return, adjusted for inflation, which means with a 3% inflation rate, essentially nothing happened to your retirement funds. They went up by the same rate of inflation. So in real, a 3% reduction, they didn't go up at all in nominal terms, but there was 3% inflation. You actually lost 3% on your funds. And retirement living expenses were pretty high. This is actually a pretty pessimistic scenario. And look, your funds run out at age 69. If you press the F9 key, you'll get another scenario. I did it again here, 19% rate of return. Retirement living's 54,000, and you won't run out of money to beyond age 101 even. Next scenario, every time I press F9, you're getting a different scenario, and you can see that rate of return is varying quite a bit, whereas the retirement living expenses are, you know, not too far off from the 50,000, but they are going up and down, just not varying as much because of that perk distribution instead of that wide-ranging, very uncertain bell-shaped curve I put in for the rate of return. So what you want to do is not sit there and press F9. You want to run a simulation. You want to do a lot of these. If you turn off the random simulation, it'll just go back to its initial settings. This little button here gives you simulation settings. And the main thing that I want to change here is if you go into sampling, there are some settings, different methods that could be used. You don't have to worry about changing the defaults on that, but this is one I would pay attention to. If you let the initial seed be chosen randomly, the computer will generate different answers every time you run this model, which is kind of comforting because it's supposed to be a random simulation. It shouldn't come out the same if it's really random. Computers cannot generate truly random numbers. What they generate is what's called quasi-random numbers. They look random, they act random. As far as you can tell, they're random, but they're not random because the computer can't do anything randomly. So it has a random seed value that it uses for some algorithm for generating these. If you want to be able to compare results, and if you want to compare your results to the ones I'm getting, I would go and change this to a fixed value. And you can put any number you want in. I'll just leave it on 1. This means every time you run it, you will get the same results, which is nice. It's nice if you're presenting to somebody, know ahead of time exactly what the numbers will look like. You made up your PowerPoint slide based on what the results showed. At the same time, there's something discomforting about it in that it's supposed to be a random simulation. Why is it always coming out the same? Well, so you have to choose which you want. It's nice to have it show up as random, but at the same time, then the numbers are going to be different every time. I'm going to fix it at 1, the random seed, just so that everybody, so if you want to run it, you should get the same numbers as me. You could have, in that box, you could have changed it, or you can change right here, the number of iterations. You should run generally at least 10,000 simulations. Computing power is no problem on this, especially on a simple model like this. There's no reason to run so few iterations that if you ran it with a different random seed, you might get very different numbers. 10,000 usually will give you pretty stable results. So all you have to do is press Start Simulation. This window pops up. It's going to actually show after it initializes this model, gets it ready to run. It's going to actually start filling in a graph of what happens as it runs 10,000 of those F9 simulations. Every time it's just going into those two distributions, drawing out values. And there's what happens for 10,000 of them. So what you can see on this, the histogram, is the funds never run out below age 65 because we don't allow you to take money out of the fund until your retirement age. And I guess the rate of return, starting at age 30, the rate of return is never bad enough for enough years that you actually run out of money before you retire. That's at least comforting. You can at least going to last until you retire. In truth, there's no guarantee that would happen. So one of the advantages of the simulation here is that instead of saying will it last till 81 or not, I mean, all the possibilities are being accounted for, including the possibility that the funds won't even last until you retire. But under these circumstances, that never happens. There is, though, about a 6% chance that you will run out of money as you retire. This big bar up here is as far as the model goes to 101, and it looks like there's almost a 50% chance, looks a little bit lower, like 47% chance, that your funds will last basically as long as you live. So half the time, you don't have to worry about it, but here are those various ages. You can move these sliders, so you could say, well, if 81 is my expected retirement now, how likely is it that my funds will last until my expected lifetime, 81? And it's about a 50% chance. So in this model, the way it's set up, there's about a 50% chance that you will outlive your retirement fund, which is not so reassuring. So even though there's a 47% chance it'll last as long as you live, there's actually very little chance that between 81 and 101 you'll run out of money. So it's almost sort of looking like 50% of the time you may have a problem with these circumstances, and 50% of the time you don't have a problem. You can click on this tornado chart, and it will basically talk about all of the inputs. In this case, there's only 2. How important were they in determining that objective? The rate of return has far more influence than the retirement living expenses. So it sort of makes sense to think that the rate of return would be a far more important variable. So there's a basic simulation model. You get far richer output out of it, but let's think about this a little more. One problem I have right now is that this rate of return applies to all the years equally. So when the rate of return, go back to this dice button, if it's 26%, it's 26% every year from age 30 to the end of the model, 101. So 70 years of 26% return each year. No wonder the number's too big to show up as the fund at the end of the year. You making a fortune. That's not the way uncertain returns work. The stock market goes up this year. It's not any more likely to go up next year because it went up this year as go down. 1 year does not imply very much about the next year. So each year's return should be uncertain. So when you go to this column D, all we did was multiply the rate of return times the fund at the start of the year. And I think instead of B7, a fixed rate of return, maybe here is where we should put a risk normal with a mean of 3% and a standard deviation. I think I gave it 17%. I'll check here in a second. 3%, 17%. And if you leave out the risk static, I wouldn't worry about it. Just, it's only what appears in that cell, and I think it's using the mean if you, by default, if you don't actually override it. So what I need to do now is actually copy this formula down, because as long as I put it in as risk normal with these numbers, even though it's the same formula, it will do a different random draw from the risk normal distribution in each of these years. So when I copy it down, it's not going to copy the same value for that random draw. It's going to change it each time. And one thing I want to check, because I'm not entirely sure, let's unhide those rows. It's in format. Make sure it copied all the way down. Yes, it did. Yeah, so even though when you look down this column, each of these cells has the same formula, it's not going to be the same actual random draw from the normal distribution. It's going to pick a different random number out of that distribution on each of these rows, which is much more realistic. Now the rate of return can vary each year, which in fact it's likely to. So this cell up here is actually not being used anymore. I believe if you check trace dependence, it's now an irrelevant cell because I basically have put the uncertainty directly into column D. So now we have a much more realistic model, and I should be able to run a simulation, go back to at risk, start the simulation over. Notice what it's showing is which cell it was highlighted to begin with. So this is actually showing the rates of return it used in this cell that we weren't even using. So it's actually just showing what we asked it to do, use a normal distribution. This little arrow will move you from one cell to the next. I mean, this actually, I'll come back to that one. Let's, objective year runs out, but put this in. Wait a minute. Change the graph type. There, the histogram. So this looks a little like what we had before. You'll notice we had about I think it was about a 5 or 6% chance that it would run out at age 65, but now there's no chance at 65. So you're going to be able to retire at least for a year on these funds, but there is some small chance that pretty much funds will run out right after you retire. Notice here the chance that it will last to the end of this age 101 is now not 47%, it's on the order of about 11%, or a little bit higher than that. And that's because in the first model we ran, when the rate of return was high, it's high in every year. Now it's not always going to go up. You may get 26% for a few of these years, but you might get minus for some of those years. So it's going to vary from year to year, and there's not nearly as big a chance that it will last safely to age 101. At the same time, you can see that there's a lot more probability in the range of 70 to 100 than there was before. All of these become possible because good years and bad years are going to balance each other out. That's far more realistic, and that's what's showing up in this model. So on average, it lasts to age 80 here, almost to your retirement, your expected lifetime. In fact, this still was set on 81, so it's actually a 34% chance that the funds will last longer than your expected lifetime. So actually, this is in some ways more worrisome because there's over a 60% chance that your funds will not last until your expected lifetime, which is 81 years. So that's good guidance, because now you want to go back and say, well, what can I do to change this? The most obvious thing that you do have control over is your employee contribution, which was set at 10% here. Maybe you should be putting away more than 10% if you really want this probability change. You have a number of levers here, though, and some of these parameters. You know, maybe your raise will be different. Maybe you started off with some money in your fund. You know, maybe you have more control of your retirement living expenses, and so we've made some unrealistic assumptions there. So there's some guidance to how you could follow up and analyze it further. But you get some probabilistic information about exactly how long these funds might last. And if you go to this tornado graph, there's a lot of inputs, because every year's rate of return is one of the inputs now, as well as the retirement living expenses. And the only thing I'll point out here is that when you look at the inputs that come up near the top as being the most important, they seem to be all in the sort of shortly before retirement. A couple of age 66 and 67 and 68 are also near the top, but it's the later years that seem to be the most important. So the rate of return in those later years has a big influence, which for retirement planning is important, because what that says is that this is part of the reason why people routinely, when they get near retirement, take money out of risky things like stock market and equities and put them into things like bonds that are safer, at least presumably safer. And the reason is because a lot of what happens is going to depend on those last few years. The early years, you have more time to make up or lose some of those gains that were really attractive in those early years. I think there may be a setting here. To settings, I think it's set to show the top 10. You know, let's show the top 20, get a little better idea. I thought it would show the top 20. Just look at that again and see if I... Oh no, the inputs there into 20. I thought I had control over how many, which I think there may be a setting somewhere. It's just showing the top 10 though. The other graph you can use, sometimes this is all easier to look at, is the spider graph. And the spider graph will show for different inputs how the output varies. So as the return on age 63, this red one, as it goes from its lowest value to its highest value, this is the vertical axis, is what happens to the year funds run out. And you can see that these are all very similar, which means that the return at ages 61 through 65 have very similar influences. None of those years stands out as being much more important than the other years. Those are the critical years. The top 5 are those actually ages 61 to 65. So basic simulation, I think you can see the advantage is much more detailed and useful information, I think, and realistic information about how uncertainty influences what you're interested in. In the next video, I'm going to take this quite a few steps further and have a much richer model because there's clearly more things that we can account for than just these two variables. But this allows you to see a comparison of the simulation approach to just the basic Excel tools that allow you to do what-if analysis, but without any real probabilistic information. The probabilistic information is really what Monte Carlo simulation was designed to do. So I'll stop this video here and pick it up in the next one.